everyone knows the Sudoku, right? So we want to write a Sudoku solver. We want to write a Sudoku solver, right? And everyone knows the Sudoku. I don't want to, waste the time. We have. Any question or? We have 9 cells, big cells, or I don't know, big areas, right? And then each of these guys are. Let me do this. But I wanna do these guys a little older. So we have some numbers inside of this initially, right? Let's say I wanna use the example that's, we have some numbers like this, 6, 9, 8, and we have some numbers, right? And some of the cells are empty, and we wanna solve this. And we know the rules. Each row should has only 1 to 9. We shouldn't have repetitive values. Each column also should have only 1 to 9 and without any repetitive. And each of these guys, which is 9 cells, should have 1 to 9 without repetitive. We have 3 limitations. No repeating number in any row, no repeating number in any column, no repeating number in any 9 cell square. Okay. And the question is, we have an initial value for this. Let's say, I want to write 7. Do this 7, 1, 9, 5. I can put all of them, right? We can have lots of Sudoku examples. We want to solve this, and you will see how similar, it is exactly, same pattern of the 8 queens. It is exactly same pattern of the 8 queens. So I want to go and do the really basic, the manual solution. For every cell, let's say, again, I want to go row by row. Let's say I want to go row by row. And this is my first cell. I want to put a value. How many candidates I have? 9, right? Let's say I don't have any intelligence. I don't have any, I'm thinking in the worst case, right? I have 9 options. Like we did for 8 queens. In 8 queens, we said for every row, we have 8 options. I can put my queen in column 0, 1, 2. We have 8 options. And right now, it is exactly same as that, but the context is different, right? For each cell, I have 9 options. So it reminds me, I have to do the recursive solution. Because if I put, let's say I put 1, for the remaining of the Sudoku, I have same problem, but I have 1 more filled cell. It is exactly a Sudoku problem, right? So, but exactly similar to the n queens, 8 queens, we said we have to check the validity of the number I'm putting, because I have some numbers already, right? I need to check the validity of these guys. So it means that I need is a valid function also. Is it valid or not? For example, here I want to put 3. It's not valid because I see we have 3 here. I can check this row and column, and also this, it's a square. If we have already that number, we don't need to do that. So it means that we have same structure. Let me We have same structure for our recursive call. We have a for loop for I in range 9, right? Actually 9 I can write, because we want to go 1 to 9, I have to write 1. Let me do this. 1 to 10, right? It will go 1 to 9 because their 10 is not inclusive. I will go over them as we did, and I will check if it is valid. If it's valid, what? I. If I is valid. If I'm, for the I have all of these guys, right? And I want to put this value inside of one of the cells. And the cell, in order to specify a cell, I need a row and column number, right? I want to only formulate in the, the row and column. I need row and column because I want to put I in this row and column. But instead of writing I to make it much more better, I want to write number. I want to put a number 1 to 9 inside of the row and column, but I need to check if it is valid or not, row and column. And I want to put number here, and I need to pass the board, right? We know that the board, this is our board, which is a 2-dimension array. I need to pass it because I have lots of information inside of that. So again, we have to say if it is valid. So I don't have a space here. Let me move this guy. Okay. If it is like this, I will do the same operation as I did. I will put board. I will write the code, the clean code in the next whiteboard. Board I, row and column will be none if it is valid. So I put this here, and then it's time to call my recursive function for next cell. So I will call, let's say, my helper. My helper will be board next I. The reason I'm writing next I because it is not simply I plus 1. We have, for example, if we are here, the next I is I plus 1. But if I'm here, I will be the same value. And J, we have same for J. If we are here, J will be, the next J will be J plus 1. But if I'm here, the next J will be 0, right? So that's why I'm writing, next I and next J, and then I will develop these guys. I will calculate them in top here. So I will calculate them. I will call the helper function. And that's it, this is the main idea. And after I'm doing this, same as, I want to go really, fast on the approach, but I will go and write the code and you will see the more details. But similar to the 8 queens, let me change the color. We updated this guy, but I'm calling several times because of this for my recursive function. If I'm changing the board, after this, I have to revert it because I want to try all of these guys because we are trying them. This is not the final answer. We put 1 and then we want to go and solve the problem, the rest of the Sudoku, right? And then we want to put 2 and solve the rest of the Sudoku, 3 rest of the Sudoku, right? So when I put 1, I go and solve here. And after that, I have to revert it. Let's say the initial value is empty, right? Let's say that we have a strings here and this is empty. This is, the general idea. As you can see, it is exactly similar to 8 queens. Only we have some differences in is valid. Is valid will be different. we can have lots of other questions that is valid will be different. But if you know the structure of your code, that you have a for loop, and in for loop, you need to check the validity. After, if it is valid, we need to update some value for my current cell. Right now it is cell, but even the previous one was cell, right? We wanted to put the queen in one of the cells, okay? And then call the recursive function for the rest of my problem, which is one of my sub problems, revert it because we are trying all of these values. And that's it. Let's go and write the code, the clean code here. I just wanted to show you how it is similar to the 8 queens. Any question about the approach?
How do we keep track of the numbers that are already seen? Like the ones that already are given?
Actually, this is a good question because we have some other questions. The direction, our movement, we have lots of grid problems, right? I solved, I think the first or second, online meetup. If we have, the movements right, right, left, up and down, we need to have a visited or seen array to be sure that we don't have any repetitive, we don't, process the repetitive cells, right? But here we go only in this way. Let me do this. We go line by line, right? How we guarantee this in the next I and next j. How we are traversing this Sudoku, we are traversing line by line. And the approach is, guarantees that we don't do the repetitive, we don't process any repetitive cells. But we have lots of, the grid problems. Maybe I will solve it the next session. That's, we have different kind of movements. I did, in I think this second session of the online meetups, but we use the BFS or iterative solution. Actually, we can solve them also with DFS solution and backtracking. But here we go row by row, and we don't have repetitive processing. Was that the answer for your question?
Kind of. So what I was thinking is, if you have 5 and 3, you shouldn't be trying 5 and 3 in the empty cells.
Yeah, that's why we check the is valid. I didn't write here, right? We go and we check, we try all the numbers from 1 to 9, but we check in is valid, right? Inside of the is valid, it will return true or false. If it is valid, for example, here 1 is valid right now, right? 1 is a valid number for this example, because, we don't have 1. But actually I didn't write, all the numbers here. Let's say this is valid, we put there. Does it make sense?
Yeah, and then
okay.
to do that, will we, so for each of the empty cells in the first row, we want to do that check. So should we keep a set or something to do it efficiently?
Yeah, actually, yeah, we can do the set also, but I don't want to make it really, we have some more creative solutions for this problem, but I want to go, the pattern-based, solutions, right? Yeah, definitely we can do the set, but also in order to make the set, you have to the for whole of your Sudoku to create your set, right?
Right.
You have the same, time complexity, but actually we have, especially for this problem, we have really creative solutions to decrease the time complexity. But if you have this in the interviews, if you have this solution, it is more than enough for the interview. If you did the recursive solution and they do the backtracking. Okay?
Okay, thanks.
Okay, here, perfect. No problem. So let's go and write a code. Background is this, and so let me write the top level function define solve Sudoku. And what is the input for top level? It is only one board. And the board is a matrix with 9 rows and 9 columns. And I want to return let's say I want to write again in a helper will be board. In order to call the subproblems, we need index number, right? The row number and column number. Based on the discussions we had in the previous whiteboard. So the initial will be 0 and 0. This is my row. This is my column. The starting row and starting column. So let's go and write the function define helper board. Actually, for a row and column, in order to make it, shorter, I want to write I and J. I and J. So we said, we have another difference. I didn't talk about it in the previous whiteboards. For some cells, we have already values, right? So we shouldn't do anything. Only we have to go to the next cell, right? Let's say we have 1 here. And we know that for all empty cells, we have empty string. So first of all, I want to check if board I and J, if it is not equal to empty string. It means that we have already a number inside of that. If you have already a number, only I need to go to the next cell and call the same function. So I will return helper board and next I will write the function, the calculations for these guys. Next J. Why I'm returning? Because we want to return true or false at the end. We have some pseudocodes, maybe there is no solution for them. If there is no solution, we will return false. If there is a solution, we will return true, right? So that's why we are returning. Also, we are updating the board. Actually, the answer will be inside of the board, but we are returning because it is possible to have the invalid Sudoku without it. So let me move these guys. I need more space. So how can I do the next I and next J? We need them. I will write here next I will be equal to. So next I, let's say, next I will be the same I, right? If J is less than, we have 0 to 8, right? For all of the cells except the last one, the next I will be same I. So I will write less than 8. Else, it means if J is equal to 8, the next of this guy is this cell, right? So I should be I plus 1. Okay, you can write, I did this in one line. You can do the regular if and else statements. It means that if
short question,
sure.
Shouldn't it be less than 7 instead of less than 8?
Less
So
than.
we go from 0 to 7, and you want to.
Actually, no.
This
This is you're confused with the the chessboards, right? The Sudoku is 0 to 8. We have 9 columns, right? Does it make sense?
Okay.
In the chessboard we have 8 columns, but here we have 9 columns. Okay, from 0 to 8.
Okay. Yeah.
Oh yeah.
Right.
Actually, it is normal. Even for me when when I'm doing some we mix the problems with each other. So next J will be a normal. Normally it will be J plus 1, right? So that's why I'm writing J plus 1. But if it is at the end, let's say it is 8. 8 plus 1 will be 9. But I want to have 0. So that's why I want to write a modulo 8. Yeah, actually modulo 9, sorry. So let's say we are in the J is 8, which is the last column. 8 plus 1 will be 9. 9 modulo 9 will be 0. So we'll go to the next, the J will be 0 and it's true. So I did, the next I and next J. But let's say this is not, it's not, actually it is empty and it's time to put some numbers inside of that. So that's why I want to write for num. And as you can see, we put the empty string. It is really important to be aware of these, the types. We put empty string, it means that the initial board, all of the values inside of the cells are a string. They are not integers. They are not integers, right? If you have a numbers, they are like, let's say 1, this is a character. So that's why you have to be aware of this num in. I want to put 1, 2, 3, 4, 5, 6, 7, 8, 9. It means that I will traverse 1. In the first round will be 1. The second one will be 2. But if you are doing it in other languages, I think you can do I as integer, but you have to cast this. You have to cast the I to or num to the string before putting it inside of the board. So inside of the for loop, the first step exactly, as you can see, it is so similar to the 8 queens. We will have if is valid, board, I and J and num. I want to be sure if I want to put num in the cell I and J. I want to be sure if it is valid, I want to put inside of this, so, right? So I will write board I and J is equal to num. And now it's time to call my recursive function. But we said that our recursive function returns true or false, right? If I call, let's say I put this here, right? And in I and J, and I want to call for the next cell. If it returns me the true, let's say the remaining of the Sudoku returns true, it means I solved it, right? But if it doesn't return, I have to go ahead, right? It is another difference between this problem and the 8 queens. In 8 queens, we wanted to calculate all combinations. If the question in 8 queens was that return one of the, the valid placements, we could do that exactly like this. If it is true, so return it and we are done. We don't need to do all of them. But in 8 queens, they add, the question was return all of them. That's why we don't return. We go until we find all the answers. And in the base case, we append the results in the queens, any, the valid placements in the results. But here, we have only, whenever we find the answer, we have to return it. So that's why we write if helper, we put the helper in the if statement, because if it is true, we have to return true. But if it is false, we shouldn't return it. We have to go ahead and find the answer. So that's why we are writing board next I be calculated, in the previous, in these lines, and next J. If this is true, return true simply, and the board will have the the final answer. If it is not, we call it, we need to go again. Let's say the next round, maybe we call this recursive function. So I have to revert this operation because we are trying. I'm repeating this because this part is the most difficult part to understand, you know, for most people. We are trying these values. If I'm trying something, the next round I want to try another one, I have to revert the previous one. So that's why I will do the here board will be empty, the empty string. And at the end, if let's say we didn't actually here, sorry, I will write return true. Okay, it is return true. And if we finished all of them and we didn't return true, it means that we didn't have any valid answer for this Sudoku. So it means that we have to return false. So now it's time to write the base case. I'm increasing I. When it will be finished? When I is outside of this guy, right? So that's why I want to write if I is equal to 9. I'm not talking about J because the last cell is this part, right? The last cell is here. Immediately when we have I is equal to 9, we are done. It means that we put all the valid values inside of that, right? So it means that, so we have to return true because we are done all. Okay. And this is, I think, is done. And only thing we have to write for this, you know, this problem is the isValid function. For isValid, actually, I can write in 1 or 2 lines, but here I want to go the most readable code. In my meetups, actually, I try to write more readable codes. I'm not writing fancy codes, or maybe you can find, you know, some codes on the web that, you know, they are more compact, you know, more creativity, you can see that, but, you know, code should be readable. And actually there is, and those codes that are more compact, they don't change the time complexity actually. In some cases, they decrease, you know, the execution time. But here I try to write the codes in a way that are more readable than, you know, the more, you know, fancy. So that's why let's go and write, you know, the isValid function. And I want to do really the basic algorithm, and then I will write, you know, the more, you know, more dense algorithm, more for people who are interested in. isValid, and we know the validity rules, right? If I want to put one value in a given cell, I shouldn't have any same value in its row and its column, and also its a square. And the difficult part is finding it's a square, right? We have to find the square of each cell. Only that part is a little tricky. But as I said before, please, I'm, you know, emphasizing this. Write this one before diving into isValid. Let's say I have this, and you will pass the interview. In most cases, interviewer won't ask you, go ahead and write isValid. If you go and say, okay, I have this, go ahead and build up all of your algorithm and your top level algorithm. In most cases, the time is over and you did with high self-confidence your top level algorithm. But if you have time, go ahead and, you know, solve it. If, but most cases interviewers ask you, you know, don't need to do that. Okay, but here in a board, and let's say row and column, because I want to use I and J as indices in my for loops. That's why I want to write row and column. Okay. So let's go ahead and write the first one. I want to check if we don't have any same value in its column. I need, so let's say I want to have, some example, I want to put, some value here. I want to check if there is no same value in all of these columns, right? On its column. So I need a for loop for whole rows. So let's go and write it. For I in range 9, right, from 0 to 8. If board I and a column, because column is fixed, right? We want to put in this column, and the column is equal to num, return false. This is one of the cases. We can merge all of these for loops in one for loop. It doesn't change time complexity. It decreases the execution time, but here I want to make it more readable for you guys. And later I will write, the compact all of them. I will compact all of them in one for loop. So this is the for column. And let's say I want to check if there is any same value in its row. I need again for loop for columns, and it is also from 0 to 8. For j in range 9. If board row in j is equal to num, return false. Okay, and this is the second one. Let's go and do the last one. I want to show you here how I want to find the start row and the start column of any cells square. Let's go and do this. So we have this guy. Let's say I have one cell here. I want to find, let's say I want to go like this. I want to find the starting row and starting column of the square of this guy. Well, let's say, make it a little special, let's say I want to find this guy. And I know that the starting row is this, which is 0, 1, 2, 3. And starting column is 0. Why I'm doing this? Because I have to check all the values of this cell. So I'm here. How can I find the starting row of this guy? Most of you guys maybe directly, immediately you have the answer, but I want to go really, the step-by-step is, the solution here. So we know that 0, 1, 2 should map to 0, right? All of these guys here, the starting row is 0. I just, doing the rows. And I know that 3, 4, 5 should be 3, and 6, 7, 8 should be 6, because this is start is 6, 4, 5, right? So which operation we need? Integer division, right? So if I do the integer division for, let's say 2 divided by 3, 2 divided by 3 will be 0. 3 divided by 3 will be 1. 4 divided by 3 will be 1. 5 divided by 3 will be 1. If I multiply the answer by 3, I will have 3. And for this same scenario for here, for this guy, all of them divided integer division by 3 will be 2. 2 times 3 will be 6. So I can write here, start row will be equal to 3 times row divided by 3. In Python, actually, integer division is 2 slash. start row, we have same as scenario for column. 3 times column divide by 3. Okay, so now we have this. It's time to traverse. I have the starting, you know, if any cell I have, I have the starting start index, a start row, and a start column. I need 2 for loops from start row to start row plus 3. I want to traverse 3 units to forward and 3 units to the down. Let's go and write it, and our function will be done. So here I need 2 nested loops, but you know, it is only, you know, we're only traversing 9 cells. It is not, it is exactly like, you know, the previous for loops. We traverse 9 cells, and the last one also we traverse 9 cells by using 2 for loops. I in range start row and I want to go 3 units forward. Start row plus 3. Oh, I won't have enough space. Okay, I can write a little smaller. For J, we have same scenario for columns, right? We have the starting column, and we want to go only 3 units forward. Column plus 3. Okay, that's it. And I will write if board I and J is equal to none, means we already have this kind of number, you know, this number, return false. Else return true. As you can see, it is really straightforward. I did, you know, in 3 steps, but I can write, you know, also really dense operations here, but you know, you don't need to do this kind of things in the interviews. Go based on the really more, you know, the straightforward solutions. I can go for I want to, you know, put all of these 3 for loops in 1 for loop. And put in a calculator, all the calculations will be done in some 3 conditions. I will write for I in range 9. I'm checking the first one. If board, I think I won't have enough space. Let me, board I and column is equal to none, or board row and I, because you know both I and J are going, you know, from 0 to 8. So I don't need to do, you know, 2 for loops, right? I can, you know, write, you know, here row and J. Well, not J, we don't have any J. It will be I. Or we check all of the, you know, invalid conditions. And for the last part, actually, we can do in 1, you know, operations, but you have to be, you have to do some, you know, calculations to detect this. Actually, we have, we do all of these for loops inside of the index here. We will write start row plus I divided by 3 will be the index of, you know, the starting index, and will be the start column plus I modulo 3 is equal to none. So if these guys, or of these, you know, any of these guys are correct, we return false. And that's it, you know. But, you know, I don't, you know, no interview, you know, interviewers don't, you know, expect to do really, you know, creative, you know, calculations during the interview. Go ahead and do the simplest ways, because here, big O for, you know, is valid function for both of them is, you know, the order of 9. And 9 is not a scalable, actually. It's 9, you know, 9 is not changing, right? If we say, you know, the length of the board is n, it will be order of n. And even for this guy is order of n. But the good thing for this, we do only one for loop. And that's why I'm saying, you know, the execution time for this function is 1/3 of this guy, but the big O is not different. That's why, you know, and usually in the algorithm design, you know, in algorithms, big O is much more important than the time complexity. And actually it's done. This is the Sudoku problem. As you can see, we have so similar approach. We have a base case here. Actually, the next INJ is a little specific to this problem, but you know that you have to go to the next cell. In 8 queens, we wanted to we just simply did, you know, row +1, right? Because we wanted to do the next step is the next row. Instead of this, we had row +1, okay? And in the 8 queens, we wanted to have all of the answers. So that's why we didn't have this condition. But here, actually, sorry, you know, it is for the next part. And in the 8 queens, we didn't have all, you know, initially some values. But in the Sudoku, we have some values. It is possible to have, you know, initially some values in the initial values of the Sudoku. So if you check, if we have this, simply go to the next one. We don't need to try any values because we already have a value. And after that, this part, which is the main, you know, the part of the algorithm, is exactly similar to the 8 queens. We have a for loop is valid, you know, updating, trying. Actually, it's try a new value, and here we are reverting or backtracking. So, you know, revert, or we say backtrack. And that's it. And at the end, we return false. In order to show you also, I have, you know, this is really, you know, really basic, you know, it is not IDE, but it runs, you know, my code. Actually, this is, you know, the code I write, you know, right now for you guys. And as you can see, this is the, you know, the Sudoku in line 36. This is my board, and I want to run this right now. And at the end, I print in lines 47 and 48, row by row, all of them. Let's run this. And as you can see, we have true, which is, you know, we have an answer, and all of the cells are, you know, solved actually. And actually, it's done, you know, only in, you know, a few, you know, milliseconds actually. I know the time complexity is exponential here, but, you know, the problem nature is we don't have, you know, the Sudoku with, you know, 900, you know, rows and columns in practice, right? Usually we have 9, and even when it is done in, you know, less than, you know, in 100 milliseconds also, it is acceptable. And the time complexity for this will be, we have, let's say, for each cell, for each empty cell, we try 9 elements, right? And for all of them, we try 9 elements. So we are multiplying all of these guys. 9 elements. This is like, you know, the calculating the number of the permutations. How many? This is the, let's say we have M empty cells. For each of them, we have 9 combination, and we try all of them actually. But actually, in practice, we don't try all of them, right? Because we have an is valid function. But when we are writing the big O, we are going in the worst case, because calculating the tighter bound for big O needs more calculations. And it is enough for you guys for the interviews. We have 9, and we say, let's say 9 also is n. This is the size of our Sudoku. Let's say we can define, the Sudoku with, let's say 20 rows and 20 columns. Not 20, I don't know. We have to define it should be the multiple of the 3, right? So let's say we have n, so we'll have n power m. N is the length of board. M is number of empty cells. But we know that this is a not really good big O. It is definitely, we have tighter values, right? And this is the time complexity. So I want to emphasize that big O is an upper bound, right? For example, if you say, but the big O, if you have a tighter bonds, it will be better calculations. But it is really difficult to calculate all of the valids, because it depends on the input. It depends on the initial values in Sudoku. We don't know. It is not possible to calculate the big O based on is valid function, because is valid, it strongly depends on the input, and input is different, so we don't have any other option than saying that the big O is n power m. And what is the space complexity? Any comment for space complexity? Let me check the guys here. Any comment for space complexity? We have some, I think. Oh yeah, okay, I'm doing it right now. In result storing multiple valid answers, yes, I answered this, and when we reach to this, it is 1, yes, it is true. Can you do yes, exactly, I'm doing the time and space analysis, right? Okay, so I'm doing the for the Sudoku. So time complexity is n power m, but actually n is 9 for, it is better to write 9 power m, and m is number of empty cells. In standard Sudoku, we have only 9 rows. What is a space complexity? We have a recursive function, right? We have a recursive function. We don't use any extra memory, right? Board is input. We don't use any extra data structure to solve this problem. But the only thing we should worry about that is stack space, because we are doing the recursive calls, right? But actually for time complexity, I forgot something here. If we be really more picky here, n power m, 9 power m, and for each of them, we check the is valid. In is valid, we do the 9. We have the 9 or n, the order of n for the check the validity. So it will be 9 times 9 power m, or n times power n. But again, it will be q, actually not, I'm saying q, 9 plus m power m plus 1. In terms of big O, we don't write this guy, we write in a q 9 power m. But in the more accurate, it will be 9 power m plus 1. And here, let's say n power m plus 1. Because we do for each of them is valid function, right? How many levels of recursion we have? This is the answer for the space complexity. How many levels we have? So let's go ahead and check here. For each I and j, what is the steps? The next I and j is only the next empty cell, right? So it means that we have the depth of our recursion tree will be the number of empty cells, will be order of m. Okay? Because at each step, we go to the next cell. And, we go, it is like, the recursion tree is only, like this. It is like a chain, right? We start from this and go to the next cell, next cell. We don't have branches, 2 branch. And it is order of m for Sudoku. Let's go ahead and do that for time and space analysis for 8 queens. Any idea for 8 queens? So for 8 queens, 3, 3. Oh, let me, I didn't really organize. I mean, I think I can go to the first slide. Okay. How many recursion calls we have here? Oh, sorry. For the first row is n, right? N or 8. Let's say n times. How many recursions we will have for the next one? Definitely it is less than n, right? It is n minus 1 or n minus 2 or so. It is something, n minus something, right? And again, we will have less than. Row by row, it will be decreased. At the last one, definitely we will have 1. Actually, it reminds me n factorial. But actually, it is less than n factorial because we don't go, actually, the first one is 8. The second one is not 7. It's less than 7. But we cannot, as I said, the calculation of the, even, I said in Sudoku is really difficult to calculate because it depends on the input. Here, actually, we can calculate it, but it is really complicated. But in terms of big O, you need to calculate really upper bound. And we know that n factorial definitely is upper bound. If we have a rook here, let's say we have a rook. If we put, instead of queen, we have a rook here. If we have here, the next item will be 7. I will put here 6. For rook, it is exactly n factorial. But for queen, we have more limitations. Definitely it is less than n factorial. It is really difficult to calculate it. I actually, honestly, I didn't do that. That's why we say the big O is n factorial. Maybe some guys, calculated this before. I don't know. N factorial. And what will be the, and there is again another delicate point here. We have also is valid for all of every row, right? For every function. And what is the is valid? Or we have actually, the copying of these guys. But, the is valid is much more important. And the is valid also is order of n. We have a for loop with order of n. So it will be n times n factorial. If we want to be more accurate. N times n factorial, because is validity also has its, time complexity. And what will be the, let me bring the code, okay. What will be the space complexity? we use queens, right? We use queens, but it is for, developing the result. So that's why, again, we have to focus on recursive, the stack space. How many levels we have? We go row by row, right? Again, in order to find, the number of levels, you have to check your variable. How we are changing this row by row. How many times we will call this number of rows. So this, it will be order of n. So let me write this guy here. It is a little, or I can go to the last slide, last whiteboard to write the time complexity and space complexity for 8 queens. For 8 queens, or actually, let's say I'm writing n queens. So time complexity, time will be order of n times n factorial. And the space will be order of n, which is stack space. Because if you go to the decision tree, the first time, we have 8, and this is the row 0. Row 1, we will have some, in the depth of your recursion tree will be 8, which is n. And that's done.